In the search for physics beyond the standard model, one of the most compelling targets is the mini-charged particle. These are hypothetical states of matter that carry only a tiny fraction of the electric charge of an electron, making them excellent candidates for dark sectors and dark matter. This schematic shows kinetic mixing, the mechanism that creates these particles. A hidden gauge field interacts directly with the standard model hypercharge, denoted as B mu nu, which is the mathematical field strength tensor for the electromagnetic and weak forces. When these fields mix, the hidden particles acquire a small, effective fractional charge under standard electromagnetism. But there is a glaring problem with how these particles are usually modeled. In the standard equations for massive Dirac fermions, the mass of a mini-charged particle is treated as a free parameter inserted entirely by hand. Without a specific physical symmetry actively protecting that mass, quantum corrections will inevitably drive it up. The bare mass will naturally inflate to the extreme cutoff scales of the entire theory. A cutoff scale is the ultimate energy limit where a current physical theory stops working, such as the grand unified theory scale or the Planck scale, where quantum gravity takes over. If a mini-charged particle sits at the Planck scale, it is billions of times too heavy to ever be produced in a terrestrial laboratory or observed in astrophysical surveys. The phenomenological model breaks down. For these particles to exist in observable reality and be light enough for us to detect, there has to be an undiscovered theoretical mechanism shielding their mass from this massive quantum inflation. A proposed solution introduces a new, unbroken chiral gauge symmetry, designated U1 sub x. A chiral symmetry treats left-handed and right-handed particles differently, which strictly forbids the mini-charged particles from possessing a bare mass term at high energies. These particles only acquire mass at much lower energies, when this exact symmetry is spontaneously broken by a hidden dark Higgs field. The dark Higgs field condenses into a baseline state, generating a small, highly suppressed mass that is perfectly shielded from extreme quantum corrections. Using a chiral gauge theory comes with a severe mathematical cost. It introduces quantum anomalies into the system. A quantum anomaly occurs when a classical symmetry is broken by quantum mechanical effects, rendering the resulting physical theory mathematically inconsistent and invalid. To ensure this chiral model survives as a valid quantum theory, the sum of all these internal gauge anomalies must perfectly cancel out to exactly zero. Building a consistent physical model of mini-charged particles now hinges entirely on satisfying a rigid, unforgiving set of mathematical equations. In this specific framework, there are three distinct anomaly cancellation diagrams that must be resolved for the combined U1 sub h and U1 sub x symmetries. These are the three mathematical anomaly equations governing the system: the graviton U1x, the U1x cubed, and the U1x squared U1h anomalies. The variables a sub I and b sub j represent the distinct chiral charges for our two sets of interacting Weyl fermions. Because the original U1 sub h symmetry acts as a vector-like force, treating left and right-handed states equally, the first and third anomaly equations are mathematically identical. The constraints simplify considerably. The sum of the chiral charges, the sum of their squares, and the sum of their cubes must be perfectly equal between the two fermion sets. Finding valid sets of integers that satisfy these simultaneous, nonlinear conditions requires immense computational effort. We also must exclude any solutions where the two sets share a common element, ruling out any trivial copy-paste configurations. Verifying this quantum field theory now requires solving a classic problem of Diophantine equations, polynomial equations that strictly require integer solutions. These specific conditions exactly match a historical puzzle in pure mathematics, the Prouhet, Tarry, Escott problem. This equation shows the formal definition of the PTE problem of degree k equals 3. It asks for two distinct multisets of integers, a and b, whose power sums match exactly for the first, second, and third orders. There is a strict mathematical limit to the Prouhet, Tarry, Escott problem. Finding a valid solution for any degree k requires a minimum of k plus 1 elements in each set. We can map this absolute mathematical boundary directly onto our physical chiral charge variables, A sub I and B sub j, which represent the particles in our anomaly equations. Since our physical model requires matching power sums up to the third order, k equals 3, therefore the absolute minimum number of integer elements in each set must be 4. This pure mathematical limit directly restricts the phenomenological construction of the particle sector. Number theory dictates that any consistent hidden sector in this framework must contain a minimum of 4 distinct mini-charged particle mass states. To understand the masses of these particles, we have to isolate the minimal ideal solutions, cases where the number of particle elements is exactly 4. We use a technique called an affine transformation, shifting all the integers in a set by a constant mathematical value to map and organize all possible equivalent charge assignments. This table displays valid, minimal, anomaly-free integer sets that solve the k equals 3 problem. Look at the first row. Set A contains 0, 4, 7, and 11, while set B contains 1, 2, 9, and 10. If we apply an affine transformation and subtract the mathematical center point from each of these integers, a mirrored structure appears. The transformed sets resolve into plus or minus pairs for both A and B, proving they mirror each other exactly around 0. Exhaustive computational scans confirm that up to an affine transformation, the vast majority of all minimal integer solutions to the Prouhet Tarry Escott problem inherently possess this exact symmetric property. The mathematics forces the underlying quantum charges of these 4 particles to organize into perfectly mirrored symmetric pairs. We can now plug these theoretical charge assignments directly into the physical mass matrix of the many charged particles. This grid shows the 4x4 fermion mass matrix, its elements scaling based on the charge differences. By applying a basis rotation, we group the symmetric pairs into parity-even and parity-odd combinations. Consequently, all off-diagonal elements cancel to 0, splitting the matrix into 2 block diagonal sections. In the hierarchical limit, where the vacuum expectation value, or the baseline average energy of the dark Higgs field, is very small, these 2 distinct matrix blocks become effectively identical. The symmetric nature of the Prouhet-Tarry Escott solutions guarantees that the mass eigenvalues organize into pairwise degenerate states, completely removing mass as a random free parameter. This mathematical derivation carries immediate physical consequences for experimental particle physics and the colliders actively hunting for dark sector signals. This chart plots the distribution of mass hierarchy exponents. It displays the exact mass structures produced by every mathematically sound configuration. Look at the dark bars. Approximately 85% of solutions perfectly align with a distinct doublet structure, sharing the exact same mass suppression. In a real physical system, introducing random complex coefficients might disrupt this perfect symmetry. But singular value decomposition data demonstrates that even with random coefficients, the mass ratio of the 2 states still clusters tightly near a value of 1. This specific spectral prediction alters how next-generation dark matter detectors will target their searches. Previous observational models assumed that mini-charged particles would appear as isolated, solitary blips in the data, but anomaly cancellation demonstrates otherwise. The discovery of a single mini-charged particle mathematically guarantees an identical partner particle sitting right beside it in mass.